So now we're going to do the hard work, where we're going to try and show that the joint characteristic function can be split up into the mean of this term and the mean of this term. So essentially we want to be able to express this as the product of the characteristic function for s of t1 to t2 and the characteristic function of s of t3 to t4. So if I look at the mean value of e to the ix1 multiplied by the increment from time t1 to t2, what I have here actually is the sum, right? So the sum for j equal to s of t1 plus 1. Sorry, not s of t1 plus 1, it's n of t1, so the number of claims at time t1 plus 1 up to time t2. I add the claim sizes. And then I multiply by e to the ix2, and then what I have here is the sum of j ranging from n of t3 plus 1 to n of t4 xi. Now, what can I do with this thing here? Well, I can condition on all the information that we have up until time t4. And since the Poisson process that we're working with, well, we're working with a Poisson process and it has independent increments, then it's a smart idea if we condition not on n of t1, n of t2, n of t3, n of t4, but instead on n of t1 and then the increment n of t1 to t2, and then the increment from t2 to t3, and then the increment from t3 to t4. Okay, so I condition on this, and then I take the mean outside of all of this, right? So what I'm using here is just the property of double expectation. An expectation of something is equal to the expectation of that something conditioned on something else, and then I take the mean outside of all of it with respect to whatever I condition on. So this is the property of double expectation that we will use again and again and again. Now, if you look at the solutions that have been uploaded, the answer for this exercise is extremely short. Basically, it just lists all of the things that we get from the Cramer Lundberg model, that the x's are id given n because the x's are independent of n, and so on and so on, and then basically we're done. But because we're still quite new to working with these conditional expectations, I want us to look at this at a very concrete level. So we're actually going to perform all of the calculations that lies underneath the talking. So bear over with me. This will be a long calculation, but on the other hand, I think this will help you guys a lot in being able to solve exercises on your own in the future. Okay, so I'm taking the expectation of the stuff that's in here, right? And the stochastic stuff. What's the random stuff? Well, the random stuff is that the claim number at time t1 or the increment from time t1 to t2 and so on is random. I don't know which value this takes or this takes or this takes or this takes. So when I take the conditional the expectation of this conditional expectation here, basically what I'm doing is I'm saying, well, for each outcome I can have of this and this and this and this, multiply by the probability that those outcomes will appear, and then sum for all of those different outcomes. So I actually have I actually have 4 sums that I need to have when I calculate this expectation. Now, due to certain independence assumptions, a lot of those sums will disappear. But in the beginning, let us just start by working with all of those 4 sums. So what I have first is I will take the probability, yes, that n of t1 is equal to k1, and that n of t1 to t2 is equal to k2, that n of t2 to t3 is equal to k3, and that the increment from time t3 to t4 is equal to k4. Now, actually, just to unburden the notation a little bit, let's just call this entire thing event star. Okay, good. So then I just continue writing here. What I see then is that the probability of star multiplied by the conditional expectation of e to the ix1, and then the sum of the xi from, well, I should write xj here, sorry. The sum of the xj from n of t1 plus 1 to n of t2, and then eix2, sum of xj from n of t3 plus 1 to n of t4, given star. And then I want to sum this for all the outcomes of k1, k2, k3, and k4, and since all the increments are cosine distributed, k1, k2, k3, and k4 can take on values from 0 to infinity, all of them. So equals 0 to infinity, equals 0 to infinity, equals 0 to infinity. Okay, and now the next thing we'll have to do now is to recall what is the conditional expectation of a stochastic variable given an event. Because star here is the event that the increments take on each specific value, discrete value. So star is an event with more than probability 0. So let us just recall that given a stochastic variable x, then the conditional expectation of x given an event a. So this is an event, not a stochastic variable, and this is a stochastic variable. So this thing here is equal to the probability of a to the minus first multiplied by the mean value of x restricted to the event a, which we write by multiplying the indicator of a onto x. So this is very useful to have when we want to calculate whatever we have in our expression here. So this is equal to, well, it's equal to a shitload of sums first and foremost. So 4 sums. And I'll just write k1, k2, k3, and k4. And you guys can just remind yourselves that each of these go from 0 to infinity. So 4 sums, and then I have the probability of star, which we recall was given as 4 events intersected that depend on the increments. And then I have the mean of something here given star. So as we see here, the event that we condition on in the side here, the event that we condition on, we have to take the probability of that and divide by it. And since we condition by star, we will divide by the probability of star and then multiply by the expectation of of the variable we're looking at, which is e to the ix1 sum of xj's for j going from n of t1 plus 1 to n of t2, and then multiply by I to the ix2, and then the sum of xj's for j going from n of t3 plus 1 to n of t4, and then we restrict this to the event star. Yes, where the event star is the event that n of t1 is equal to k1, and then the next increment is equal to k2, the next increment is equal to k3, and the next increment is equal to k4. Okay, so first and foremost, these two things, they just cancel, so that's nice. Basically, we can just write down as a rule of thumb now, I guess you guys are pretty used to it now, that whenever I take the mean, no, never mind. Let's just continue. We'll take the rules of thumb later on. So, okay, now I've eliminated this part here, and I need to figure something out about this thing. Well, if I have an indicator that tells me something about which values n of t1, n of t2, n of t3, n of t4 can obtain, then I no longer need to write the n's in the bounds for the sums here. So I can actually replace the n's with the appropriate values of k. So how do I replace them? Well, let's start by looking at the first sum here. So we're going to sum the xj's, right? And in the event star, we want n of t1 to be k1. So j will start in k1 plus 1. And then we say from n of t1 to t2, the increment in claim amount is k2, which means that n of t2 here in the upper bound should be k1 plus k2. So that was good. And then we multiply by e to the ix2. And here we have yet another sum of xj's. And I have to write the xj a bit farther away now because, well, we start in n of t3 plus 1, right? Now n of t3 is given by n of t1 plus the next increment and then the next increment. So it's given as k1 plus k2 plus k3 in this case. And then plus 1, because I also have n of t3 plus 1 here, plus 1. And then I let the sum run up to n of t4, which in the event that I restrict to here, the star event, well, that tells me that n of t4 must be given as k1 plus k2 plus k3 plus k4. And then afterwards, I multiply by the indicator of the event that I restrict to. However, now, note that I can actually take the indicator function outside of the expectation here, so I can split the expectation into a product of the expectation of something that has to do with the x's and the expectation of something that only has to do with the n's, which is what the event star is built on. And why is that? Well, that is because that in the Cramer Lundberg model, CL, well, we assume that the xi, so the claim size process, xi, is, or the claim size process x, is independent from the claim number process n. And because of that, because of the independence, we may split the expectation up into two products. Now, the next part, we will utilize that the Poisson process has independent increments. And And because the Poisson process has independent increments, what we may do is we may take the event star, right? And then we can take its indicator and split the mean of that up into, furthermore, 4 products of means, each depending on its own increment. And that is really nice. And why is that? Well, that is because then we can start working with stuff like this. Let's see here. You know what? Just not add too many steps at a time. We'll start by still keeping all of the sums out here. In a second, magic will happen, but until then, we'll just start by doing some legwork here. So we have the mean value of the indicator function of n of t1 being equal to k1. Well, let's just write the probability now, because the mean value of an indicator function is the probability of the event. So the probability of n of t1 equal k1. And we're splitting up the mean value of this indicator still. So independent increments allow us to write the next mean of the indicator of the next event in a separate term. So the probability of n from t1 to t2 being equal to k2. And then we continue. We have the probability of the next increment being equal to k3, and then the probability of the next increment being equal to t4. Okay, so basically what we've done now is we've tackled this thing here. We've just split the heck out of it. Forgot to write k4 here. Equal to k4. And now we have to try and figure out what on earth we're going to do with this term, right? So let's just think a little bit about it. What else do we know about the x's? Well, we know that the x's are IID. So x's are IID. So the xi's are independent, and they are all based on that they all have the same distribution. And what we see here, up here as well, is that none of the terms in the exponents for the x's are overlapping. They have no overlapping terms. We are completely safe. Even if k3 is equal to 0 for some weird reason, then we are actually also completely safe because we have a +1 here, right? So there is no overlaps between the different xj's and the sums, and that means that that the term here, this term, is completely independent from this term as well. And because of that, we may split the expectation up into a product. So we have the expectation of e to the ix1, and then we will have the sum of xj's from k1 plus 1 to k1 plus k2. But then we notice another thing, which is that the xj's have the same distribution. So because they have the same distribution, we may actually, well, what we essentially have here is the product, right, of e to the ix1 and then xj for j equal to one thing, and then multiplied by e to the ix1, xj equal to the next thing, and so on. And in that product, we have how many terms? We have k2 terms. And since all of the xj's are neutrally independent and they have the same distribution, we just have the same mean multiplied onto itself k2 times. Okay, this is very nice because this has helped us eliminate the k1 from one of our terms. And since there are no overlaps between the different terms in the sums, we have now split up the expectation into two terms. And I have, well, if we look at here, we have, again, that we have taken just the mean of e to the ix2 of the claim size x1, and we multiply that upon itself k4 times. since this sum up here has K4 terms. Oh wow. Okay, so we've used quite a lot of stuff here, and the next step will be where the magic happens. So the nice thing now is that we can see that we can actually split the sums up into different products. So let's just look at the sum first of all that lets K1 run from 0 to infinity. And look at our expression inside here, inside the sum. What depends on K1? The only term that depends on K1 is the probability that n of T1 is equal to K1. So we can just take this completely out of the rest of the sum expressions. Okay, now let us also take a look at K3. And the reason why I choose K3 is because we kind of noticed that there is also only one term that depends on K3, and that is the probability that the jump in claim number from T2 to T3 is equal to K3. So we can also take this outside of the rest of the expression. And let's see what else we have. Well, then the thing that we have left, essentially, is the sum of K2 equal to 0 to infinity of the probability of, and now we just take everything that depends on K2, so the probability of the increment in claim number from time T1 to T2 equal to K2 multiplied by the characteristic function of the claim size x1 to the what power? To the K2 power. Okay, so that's a term for itself as well. And then multiplied, getting a bit tired here, multiplied by the sum of K4 going from 0 to infinity of the probability of n of T3 to T4 equal to K4 multiplied by e to the multiplied by the expectation of e to the I x2 multiplied by the claim size, so the characteristic function of the claim size to the K4. Okay, so what do we notice here? Well, first of all, the term where we sum over K1, that is just equal to 1. Because I'm summing the point probabilities from K1 equal to 0 up to infinity in a Poisson distribution. And that just gives me probability 1. And the same goes for the sum over K3. So we've eliminated the part where there is K1 and K3. And what we're left with is the product of two sum expressions. And let us just scroll up and recall the characteristic function of the total claim amount from time s to t. That is given as the point probability of increment in claim size from time s to t multiplied by the characteristic function of the claim size to the k. And that is exactly what we have down here. So we recognize the characteristic function of the increment in total claim amount from time t1 to t2. This first expression that depends on K2. And the second expression, where the sum depends on K4, we recognize the characteristic function of the total claim amounts increment from time T3 to T4. And now we are home safe, because now we have finally shown that we can split up the joint characteristic function of S from T1 to T2 and S from T3 to T4, that we can split that up into a product of each of the characteristic functions. And now I know this proof is quite long, quite technical, but please take a look at it again and again and again, because even though the answer in the solutions that has been uploaded by PDF is shorter and seems more elegant, you truly do not know what that answer means before you have been through these kinds of calculations at least 2 or 3 times. So just take a look at this, and it will also give you a better intuition of what conditional expectations in the discrete case are all about.